Hi all, this is the third part of kinetic and equilibrium. In this video, we will focus on chemical equilibrium and Le Chatelier's principle. Chemical equilibrium. Chemical equilibrium exists when the forward and reverse rates of a chemical reaction are equal. As a result, the concentration of the reactants and products remain constant. For example, this equation represents a chemical system in a state of equilibrium. Châtelier's principle. When a system at equilibrium is subjected to a stress, the system shifts in order to relieve the effects of the stress and restore the equilibrium condition as closely as possible. What is a chemical shift? Any chemical reaction can proceed in only two directions, forward and reverse. When a reaction responds to a stress, either the forward or the reverse reaction will take over temporarily, and we will observe an increase in the production of products or of reactants. A forward shift is called a shift to the right, a reverse shift is a shift to the left. To understand Le Chatelier's principle, we will use the production of ammonia by the Haber process. At equilibrium, the rate of ammonia production equals the rate at which ammonia is decomposed into its elements, and the concentration of nitrogen, hydrogen, and ammonia are constant. Of concentration. Concentration is expressed in moles per liter. Concentration is expressed by placing the symbol for the substance in square brackets. For example, bracket start NH3 bracket closed. When the concentration of a reactant or a product is changed, the system will shift in order to restore the original concentration as closely as possible. Suppose concentration of N2 is increased in the example of the Haber process. Since nitrogen has been added to the system will shift to the right in order to remove some of the additional N2. As a result, concentration of ammonia will increase and concentration of hydrogen will decrease because it is needed to react with the nitrogen. Eventually, a new equilibrium point is established. Reaction in which one of the product is continuously removed will never achieve equilibrium because the reactants will be used up in effort to replace the disappearing product. An example of this is the laboratory preparation of hydrogen gas by reacting zinc with hydrochloric acid. Since hydrogen continuously escapes from the reaction, equilibrium is never attained. This reaction is said to go to completion, and we will write this equation with the familiar single arrow. Effect of a change in volume. In general, a change in volume is accomplished by changing the pressure on a gaseous system. An increase in pressure leads to a reduction in volume and vice versa. Reducing the volume by increasing the pressure brings all the particles into closer contact. This stress is relieved by a shift that produces a smaller number of particles. In contrast, an increase in volume leads to a shift that increases the number of particles present. Let us consider the Haber process, where nitrogen reacts with hydrogen and makes 2 mole of ammonia. The left side of the equation contains 4 mole of particles, 3 mole of hydrogen and 1 mole of nitrogen, and the right side contains 2 mole of particles, NH3. A shift to the right reduces the number of particles. Suppose the volume of this system were decreased, causing the pressure to increase. The system would shift to the right in order to decrease the number of particles present. Concentration of NH3 would increase and concentration of nitrogen and hydrogen would decrease. If the number of particles are same on the both sides, then a shift in either direction would not relieve the stress. Example, hydrogen plus chlorine equal to 2HCl. Changing the pressure by adding an inert gas. The pressure of an equilibrium system can also be changed by adding an inert gas. Suppose we had helium gas to the N2H2NH3 system. Since helium does not react with any of these substances, it would have no effect on the equilibrium of the system. Of change in temperature. When we raise the temperature of a system, we do so by adding heat to the system, and when we lower the temperature of a system, we do so by removing the heat from the system. When we lower the temperature of system, the rate of both the forward and reverse reaction will decrease. According to the Le Chatelier's principle, the system will shift in order to relieve the stress. If we lower the temperature of a system, the system will try to replace some of the lost heat. Since the exothermic reaction releases heat, it will be favored. If we raise the temperature of a system, the rate of the reaction of both the forward and reverse reaction will increase, but since endothermic reaction absorbs the heat, it will be favored more. Let us consider the Haber process. In this process, the forward reaction is exothermic. So when the temperature of the system is raised, the reaction will shift towards the left and the endothermic reaction will be favored, and the NH3 concentration will decrease and the concentration of nitrogen and hydrogen will increase. If you lower the temperature of a system, the system will shift to the right and the concentration of nitrogen and hydrogen will decrease and the concentration of NH3 will increase. Effect of a catalyst. For a system in equilibrium, the presence of a catalyst increases the forward and reverse reaction rates equally. Therefore, no shift in the system will result. If the system is not in equilibrium, a catalyst will shorten the time needed to reach the equilibrium. Here is a summary of effects. Our next video is on the equilibrium constant, so don't forget to like and subscribe. Bye for now.